Welcome to the lecture series on object oriented analysis and design. We are looking at one of the most difficult aspects in object oriented analysis and design, namely object identification and modeling. This idea of modeling is exclusive to object design, something which is very specific. We have positioned object oriented as a paradigm, and one of the techniques, handful of techniques are there for object identification. One of the techniques is behavioral analysis. This behavioral analysis is banking on an old idea. It is not something which is new, neither is it specific to object oriented, but then suddenly we cannot show success in a completely different paradigm without banking on the experience and the skills that are acquired up to that point in time, and we can't do things in vacuum. The idea of defining a paradigm is not to position it in complete isolation, but giving it a capability of drawing from the lessons learnt until now and then couching it in a set of terms that keep our focus on the new paradigm that we are talking about. It is a paradigm shift. So, data flow diagrams were known to us for quite some time. People have attempted, people tried to build data flow machines. However, the von Neumann architecture and the way we have been talking about programming has stuck. We do not find too many people working in the data flow idea. The idea was there long time back. Data flow machines were always being spoken of, but then they were neither commercial success nor succeeding in so many numbers or real challenging problems. We do not have to do so many things differently to get maybe a marginal improvement on what this machine can give. However, the moment we started talking about object oriented, we started looking at data flow as an idea. We begin the exercise of programming with a well defined input data and a well defined output data, and we want to somehow unravel how this well defined input data is transformed into the well defined output data. This has been the goal of programming, and we simply call that as a function f, which transforms the well defined input into a well defined output. The quest for finding function f has been different in the way we have been talking about software engineering, or as a matter of fact computer science and engineering. It is not so mathematical, it is not so scientific than what it is. That is a story which we have been trying to understand for 6 to 7 decades, but the roaring success of a field in such a short span of time is something fascinating. So, what we need to understand is that while defining input and defining output, we have been making some progress. Writing up this transform has never been so easy, it has been very tricky. Why? Because at every step in transform, we do not need the full well defined input and the full well defined output to compare immediately. Overall, this well defined input must be transformed into the well defined output. Let us say 10th statement from the start, only some portion of the well defined input will be considered. It may lead to output, it may not lead to output, or it is only drawing from the earlier transformation. So far, we do not know the dynamics of that function f with the clarity unless you start talking about, like we began in program engineering, a test case. For this particular input, this is how the output is coming. However, we are not at all doing that kind of an exercise of looking at the well defined input in full entirety. Is it getting transformed into the well defined output in its full entirety? Whenever we want to find out in the process of transformation is a big question mark. So, what we did was said let us address this from the data flow. The data is there, how is it flowing into this function or into this set of instructions to get the output? If I can understand how the data flows are happening, then maybe I will understand how that function is better optimizable on data, optimizable on that well definedness, which we can also verify whether the input is well defined or the output is coming out as we have desired. Otherwise, it is garbage in, garbage out. That theory still holds good. So, the idea of data flow was there very early. the data flow is obvious in what we called the block structuring, which we discussed earlier on, modules and blocks. The block structuring, there is a precondition for the block, a post condition for the block. If I can derive the precondition from the post condition, then I have been telling that the block is correct, it is performing correctly. So, we tell that you do whatever you want, but give me this much, it will give that much. Now, from this can I go back to find out whether that was the precondition, then the block is correct. We can't say something is wrong with the block, because that is our precondition, that is our post condition. We have given those pre and post conditions, and from the post condition you are able to arrive at the precondition. So, we have understood the block. We do not need to know the internals of the block, much like what we have been talking about an object. We do not need to know the internals of the operation of any object here to use it. To use it, why should I know so much about how that object is? So, therefore, what is it that we have been talking about is that in the process of fixing the preconditions and post conditions, can we identify an object? There is a precondition for the object, a post condition for the object. How? From the data. We know that the object is nothing but some data and some common operations. There is common operations, common data, which is inheritable from the class, and maybe few more data items. So, since we are able to identify a class with common data, common methods, the data which are called attributes, and the methods, attributes and methods are together, every object gets these. In addition, some objects may get some more data items, some more attributes or some more methods. We can always do that. So, in the process of doing this combination of what data is working on what operations, can we recognize or identify objects? It is possible, we said. The behavioral models are used to describe the overall behavior of the system. Two types of behavioral models are available. One is data processing model, the one that I have described. The other one is state machine models that show the system's response to events. These models show different perspectives, so both of them are required to describe the system's behavior. Now, one approach which we are talking about in behavior analysis is data flow, that is what I have described. The second one is state machine model. If something happens, the machine, the entire machine should show that we are now here. The train is moving at a time called 10:30, it should have been at this station. It tells me that whether it is running late by half an hour or 40 minutes. The other things I am not concerned. A train has started here at 9 o'clock, 9:30 where is the train, 10 o'clock where is the train, where it should be. So, we have calibrated everything very nicely. We are telling that this is how it is. So, today we are able to track our letters, speed post letters, it will tell precisely where it is. It is a state, that is a state machine model that is telling us what is happening to a courier that you have booked. Today we are tracking so many things, online shopping, so many things are getting ordered. You have a tracking number, you feed the tracking number, it will tell you it has left the depot, it is starting here, it is here, tomorrow it will be delivered. We can time the deliveries, we can tell that it can be only after 8 o'clock in the night. All these things are now possible. That is easy to understand as state machine model. That is the behavior of the system. You are also talking about the behavior, but you are not talking so much about what is going in, what is coming out. But at this stage, how many pieces is the fellow who is expected to deliver holding, or how many employees who are going to deliver the goods are running on the street. Those are not the items that we are interested in. The data processing, the data flow model will talk like that. So many vehicles have left with so many data items, so many people have gone. Gradually one person with one data item or the data items that you have ordered, that is objects, the goods that you have ordered will be delivered to your office. This is a state machine model. You have a tracking number and then you find out where exactly it is. It does not matter who brings it, it does not matter which is the vehicle number that is bringing. By saying so, I am not indicating that the other model is not necessary, it is necessary, but one way of looking at it, this is another way of looking at it. Putting all these together, we created what is called a unified modeling language. We did not exclude any of these ideas. Please be careful about these lectures. None of these ideas has been excluded. We found a nice way of putting them all together and called it unified modeling language, the 9 diagrams. These models show different perspectives. So, both of them are required to describe the system's behavior, but we are contented. Typically, a user is contented with one model. I know that something is going into this place, something is coming out of it. I am very clear that this is going in, this is coming out. So, what is in between is probably like this. I will infer like that. State machine model is another way from here to here. How long is it going to take? What is the tracking? I have described that. Both are necessary. Data flow diagrams may be used to model the system's data processing. These show the processing steps as data flows through the system. For quite some time, we were not interested in finding out how the well defined input is actually going into the function. The function is there, you put the well defined input, there is a well defined output. How many test cases you can generate is up to you. If it is mapping correctly into the output, then I am not even worried about this function. Gradually we realize that after some time, for different input case combinations may come and it can lead to a disaster. So, the software engineering people have improvised beyond the program engineering to make it generic enough. DFDs are an intrinsic part of many analysis methods. Simple and intuitive notation that customers can understand, show end to end processing of data. Now, this is what we have been talking about: order processing, DFD, order details plus blank form. It is here, and then we talked about the way in which it works. So, order processing, we say that it is here, we say complete order form is here for us, and what we have been doing is completed order form is here, validate order. So, if I want to find out what is this object called validate order, I do not need to know what are the details that are filled in the complete order form, how the earlier step is happening. This is an object, it validates the order, checks what are the boundary conditions. If there is some incorrect data, it will tell. So, what we are doing, we are filling so many forms. Presently, because of the coronavirus scare, all of us are online. To register for a webinar, you have to fill 10 items. After you think you have filled, you hit the submit button, then there is a message saying that you forgot to fill the most important field. Please fill it and resubmit. That is validation step. It is not bothered about how you are getting the form, how you are filling the other details. It will only focus on what should have been filled and you did not fill. It will come back. So, what we are doing is, all of us are doing lot of registrations. Every day I am filling about 3 to 4 registrations. It is not that we do not have the skill, but then human mind is like that. We get so bored, we get so familiar, we think it is already filled. On top of it, we are having some nice facilities. The Windows operating system will remember some of the data. Whenever a form is coming, it automatically prompts me, use this data, 2-3 data items that come, I select one, it does not match. So, validate order is something which is very helpful, because we know that human way of working is like this, it is built in. Most forms for registering yourself to the webinar will have that. Validate order, signed order form, record order, only after validation the order is recorded. Then what should you get? You should get a message to the registered mail address or your mobile number saying that this is the link which you will have to use. There is, we look at it as an order. Some of the organizations who are announcing the webinars, they take it as orders, free webinar, but it is a purchase order with $0, because that is their system all along. They do not want to change the system. The overall system is for most of the times for purchase orders. Occasionally they have free webinars or free things, $0, it will come like that. So, only that recorded order will get it, and now they personalize the link. The link is not transferable. Computing is thus very interesting, very challenging, very intellectually stimulating. Based on the data that I filled on the order form, the link is personalized. Once it is validated, once it is recorded, it is a personalized link only from that mail ID, only from that machine it can be used, otherwise it cannot be used. Now, these are all matters which we have been talking about: identity, web, there are so many other concerns, but for the present please understand that wherever there is a form filling, like in the case of registering for an online event, webinar or whatever it is, you have to fill the form. If you want to purchase something from an online shop, you have to fill the form. Form filling now is the in thing. People are doing it with joy, with enthusiasm, but there will be some gaps, because suddenly the form will change for a particular brand. You think it is the old one and you start submitting, validation, erroneous data entry checks. After all that, the order is recorded, one goes to the order file, the other goes to the budget file, because if you already have the PayPal or something, it will delete that many amounts, that much of points or whatever amount it is, and then go ahead and place the order. Either you are sending it to the supplier or whatever you are doing it, this is the process which we are following. Today form filling is just there. Online form filling is being enjoyed by many people. It was not so easy till recently. Even 5 years back, people were very apprehensive of online money transfers, including me. Even I was not doing so many things on my ATM or card. 5 to 6 years is a span where the entire idea has stabilized. We got good reliability statistics. Only if necessary we go online, otherwise we simply go and purchase. Now, last 5 months everything is going online. Well, it is working, it has withstood. Technology has done the purposeful work which it was meant to do. The volume business has also caught on. Suddenly the volume has increased in this method. DFDs model the system from a functional perspective. Tracking and documenting how the data associated with the process is helpful to develop an overall understanding of the system. Data flow diagrams may also be used in showing the data exchange between a system and other systems in its environment. There is an insulin pump. This is what is called automatic blood sensor. By the way of practice, it is a culture that we need to understand. Most of these testing of human blood, anything to do with you, is considered a clinician's job, not a personal job. Well, these days we got trained, we know how to do that. It is a very simple tester. There is a blood sugar sensor. Take one drop of blood, put it in a common place. There is a small paper kind of a thing that absorbs the blood. Push it into the slot. It will tell you what is the blood sugar level. Sounds good, sounds interesting. Now we are talking about more materials, not only the form. So what is it that we are talking about is, it is true that from the input called blood and output called blood parameters, I can roughly find out what is that object that I am talking about. What is the blood parameters? I can roughly guess. It should be something like that. It does not require a supercomputer, it does not require too much of imagination. How do you put the blood? How do the blood parameters come? I know that there should be a machine and it should be hygienic enough, lot of things, a clinician's work. It should be something like a clinician who is talking about that. That is modeled, a part of it, but is it exactly equal to the entire clinician? Obviously not. It cannot do so many things. It expects that this is how the drop of blood is extracted, this is how it is put on the on that simple way of absorbing the blood, it goes in. Now, this much of apparatus is easily visualizable, provided you are in the field. Suddenly you talk to a layman, he will not be able to find this out. It takes time to get familiarity. So, all the things we have been talking about do require that idea of domain, and the entire field of software engineering, we want to shake off that domain dependency. Our analysis and design is always to shake off the dependency on the context, to shake off the dependency on the domain, to shake off the dependency on any stakeholder. We want to make it so abstract that what works here will also work in a similar condition, which we can build later, the generalization. That is the strength of software engineering. There is a little bit of a speciality. If you know the domain, somebody who has no idea about blood sugar, he does not make sense of anything here. That is why the example is here. What is insulin? I do not know. Until recently we have not understood the thermal temperature measurement. Today, every day I am getting it done 2 times, one at the gate of the quarters, one at the gate of the university. Of late it is 3 times now I am getting into EM square RC, 3 times I am getting my thermal temperature tested. It shows they put a small instrument and people are nice, the corporation people are coming and then testing, but then the fact is you should know what it is. All of a sudden if you put something and say yes you can go, do you make any head and tail of it? Now they ask the same question, why should everybody know what it is? So we started banking on the authority, saying that authority says you stand here, get this done and go, no questions asked. That is heaven. Somebody else is doing it, you are just following the order. So that abstraction of what is that exercise in its entirety is great. You do not have to tax your mind. That is precisely what we have been telling, the user should focus on his work. This is something which is happening of late, last few months. We are being halted and a machine is being put on the forehead, some metric is being said, says you go, that is all. We are nicely telling that I am not really concerned about it until there is a serious concern. Wherever you go, it is the same case today, these days. So what we did is, one way of looking at is data based, this is how data based, the other one is event state, because we do not know the domain, we can't understand what is that data. So we do not have an idea about what is this data called insulin, we do not know what is this idea called blood sugar level. So without domain expertise, data is not so much meaningful and purposeful, we can't build it as an object, we can't look at it as a method easily. It is an idea, it is a good idea. So what I am talking about in this insulin meter is changing over to scenario. What I described is a scenario. 3 times in a given day I am facing the same scenario, one at the entrance of my quarters, second at the entrance of the university, third at the entrance of the facility where I come and do this lecture. So there are 3 times, it is time stamped, so and so person has measured, finished, the matter is over. So what is the key problem here? The key problem is complexity. When we started talking about computing, we only talked about state transition diagrams. This was our way of working with computing. Everywhere it is the same case, finite state machine. There are finite states which will tell me exactly what is the position in which the machine is operating now towards solving the problem after it has started solving the problem. We somehow mapped everything to instructions. So instruction 1, instruction 2, instruction 3, whatever the instruction wants, we are supplying it from the store, that is the architecture. And if it has gone through correctly for a given input sequence, these instructions that need to be executed, we think it has done correctly all steps, no hop, skip and jump, the input is safely transformed into the output. This is what we have been talking about. What is the problem here? Complexity. The more state information, the more complex it is. See how nice it is if I simply tell that there exists an authority that will take care of this the thermometer. It is simple, it is a nice device, seamless, it is not causing me any hardship. Normally also they are entitled to stop me and check the ID. If there is an RFID meter, that should also check. My ID card is an intelligent ID card. If there is a way, if it is an automated machine, this ID card can go into that machine and it will read out lot of things. There is a chip built into the ID card, it will read lot of things. So all of a sudden we started telling that it is enough to tell that my ID card has been checked or my temperature has been checked, that is all. If you want to give more and more details, you will be getting into more and more complex exercises. Now what is happening is, one is the detail, the second is the number of events and number of states, proliferation. It is not so easy to construct a state transition for a reasonably complex exercise. State machine models, these model the behavior of the system in response to external and internal events. The trigger is an event. Some action has happened, therefore the machine has moved from this to the next step. Instruction 1 has been executed, right now it is in instruction 2, there is a jump based on the data, it has gone to instruction 10. We are all very good sequential thinkers, and most of the time we have modeled our exercise in programming as step by step execution, since it resembles the way we solve a mathematical problem step by step until quadriad demonstratum. We said that this is a good enough way of starting. We got stuck with von Neumann architecture because that does like that. The von Neumann architecture does like that. So, step by step I know where it is: instruction 1, instruction 2, instruction 3. State machine model shows system states as nodes and events, as arcs between these nodes. So, we can clearly tell that if it is in this particular state, this much of exercise has happened, or it went wrong here. When executing this instruction, it went wrong, therefore I debug. We cannot become good programmers until we know debugging. These are all called good program engineering techniques. The state is necessary, the data flow is necessary, but then putting them together has always been a challenge. Using states, we can find out some objects; using data flow, we can find out some objects. So, we think that the unified modeling language will put all these ideas together, but that is for a later lecture. So, we are addressing the most difficult aspect in object oriented analysis and design, namely object identification and modeling. We have seen 4 ways: textual analysis, state transition, data flow diagrams, domain expertise. After that, we have one more, that is the database approach. Handful of ideas are there, none of them is completely perfect. So, we know that we have to mix and match together, therefore, we progressed further, we came up with this unified modeling language. Thank you, we will meet in the next lecture.